We start today's video with a simple question. I'm pretty sure that this is a piece of cake for you, but do you know that this 2, 3, 6 triplet is actually the only solution to this equation? Without loss of generalizability, let's assume that A is less than B and B is less than C. We have an inequality to bound the value of A. A is an integer greater than 1 but less than 3, so A has to be 2. Next, we use the same idea to bound the value of B. B is an integer greater than 2 but less than 4, so B has to be 3. And this leaves no choice for C, and C has to be 6. Therefore, we have the one and only one solution. Starting with this trivial example, let's explore one of the oldest open questions in mathematics. A unit fraction is a fraction whose numerator is 1. And if we can write a fraction as a sum of different unit fractions, then we say this fraction is an Egyptian fraction, and this process is called Egyptian fraction expansion. Ancient Egyptians were already doing this thousands of years ago, therefore the name. Let's extend our original question. Does a solution always exist for any n greater than 3? Here is a trick. Because 1 is special, 1 is unity, I can multiply the 1/6 by 1 and insert our 1's expansion. Therefore, we can obtain a 5-term expansion for 1. Repeating this trick and multiply 1/36 by 1 and substitute the expansion, we get a 7-term expansion for 1. We can conclude that if n can be written as 3 plus 2k, where k is a positive integer, then a solution always exists. By the same idea, if a solution exists for n equals 4, then a solution exists for any integers, which can be written as 4 plus 2k. Let's find a solution for the 4-term expansion. By the same idea and the same increasing order assumption, A can only be 2 or 3, so let's pick 2 for now. When A is 2, B can only be 4 or 5, so let's pick 4 for now. It looks like we have to do some trial and error, but it's actually not that difficult. C being 5 doesn't work, but C being 6 works. If we trace back the depth first search, we will find 6 solutions in total. At this moment, we are done with the question. Because we proved the n equals 3 and n equals 4 case, then we prove that a solution exists for every possible n. But pay attention to the first and the fifth solution. There is actually a shortcut. There is a pattern for the highlighted part. 1 over k equals 1 over k plus 1 plus 1 over k times k plus 1. This directly proves that if a 3-term solution exists, then an n-term solution exists for any n greater than 3. This argument clearly works for any rational number. But how do we find the solution for some n as the ancestor of all solutions? Let's assume p and q are coprimes. I can rewrite it as p terms of 1 over q. For simplicity, let's use 3 over 11 as an example. I keep the first 1/11 and expand the remaining 2. Then I keep the first expansion and expand the second expansion. I can just keep expanding as integers is infinite side. The conclusion is that we can always find a solution for some n. Here, n is 7. But this solution is not juicy. I 100% prefer this one. New question. Is there a better solution than the simple naive expansion? Notice that this 1/4 is way larger than the 1/11 in the naive expansion. Perhaps we can apply some greedy strategy. Sometimes you just wish you were born hundreds of years earlier. This greedy strategy is called the Fibonacci's greedy strategy. Always choose the largest unit fraction less than the remainder. For example, 1/4 is the largest unit fraction smaller than our beginning fraction. So let's pick 1/4 as the first term. And we keep applying this strategy on the remainder until we find a solution. But Does Fibonacci's greedy algorithm always provide a solution? Suppose the first term is 1 over k, and the remainder is kp minus q over kq. Because 1 over k is the largest possible fraction, therefore 1 over k minus 1 is greater than p over q. After some basic algebraic manipulation, we see that p is greater than kp minus q. The remainder's numerator is strictly less than the original fraction's numerator. This suggests that the Fibonacci greedy algorithm will perform no worse than our naive expansion. Therefore, we can conclude that the Fibonacci's greedy algorithm will always provide a solution. But does that solution come with the smallest n? Unfortunately and unsurprisingly, the answer is no. Take 4 over 17 as example. The shortest expansion is much more elegant than the greedy algorithm's output. And we have more extreme examples, and this is one of them. To appreciate the difficulty of finding the shortest n, let's ask the reverse question. Let's find those crazy rationals that require at least n terms in the expansion. It turns out that this is also extremely difficult. It was only until 2010s that we found the case for n equals 8. And an example for n equals 9 remains unknown until today. Correspondingly, a polynomial time algorithm for finding the shortest Egyptian fraction expansion for any rational number remains an open problem in mathematics.